Hello. In this video, we will talk about inverse trigonometric functions and we will just define them. And after that, we will see a few examples and also we will actually study how we differentiate inverse trigonometric functions. And right after that, and also we will talk about their integrations. So defining the inverse, the arcsine and arccosine functions, identities involving arcsine and arccosine, inverse of tangent of x, cotangent of x, secant of x, and cosecant of x, the derivatives, the derivative of other three integration formulas. Anyway, inverse trigonometric functions arise when we want to calculate angles from side measurements in triangles. It's like sometimes like functions, right? If we are given input variable, we know how to calculate output variable. And also the question arises actually, how about if you're given output variable or output quantity, let's say, how do we find the input quantity? A similar thing for here, if you're talking about trigonometric functions, right? If we are given an angle, we know how to calculate the value of the trigonometric function. For example, let's say if you're talking about sine function, right? If we know actually this the value of the x, for example, we know how to calculate sine of x or cosine of x or tangent of x. So here we'll just actually think about the inverse procedure of this calculation. If we are given the output variable, right, how do we restore the input, let's say, value? So anyway, we know that to define the inverse function, the function must be a one-to-one function. And the sine, cosine, tangent functions, they are periodic functions. And just a second. Periodic functions, and they are not one-to-one over their domain. But if you just bring some restriction to their domain, right, they become a one-to-one function. For example, this, if you look at the first graph, that's the graph of the time function over the interval from minus pi over 2 to pi over 2 inclusive, right? And there, if you draw any horizontal line through this line, right, it is actually, there's maximum one intersection point with the graph of this function, which means that this graph is the graph of a one-to-one function, that is sine function. So now you can say the sine function is one-to-one function over the interval from minus pi over 2 to pi over 2. And over this interval, right, the function actually assumes every value over the range, this negative 1 to 1. So how about for cosine function? It's, we know this even function. If you just actually define this over the interval like sine, for example, from minus pi over 2 to pi over 2, and the function's graph is not the graph of a one-to-one function. But if you consider the constant function over the interval from 0 to pi, you see here the graph is, if you draw any horizontal line, right, that is one-to-one function. So that's why we can actually define the inverse of cosine over this interval then, because over this interval 0 pi, right, we know the range of the cosine function is from minus 1 to 1 inclusive, right? So 0 to pi, at every point it assumes all the values from negative 1 to 1. In a similar way, also for tangent function, if you consider this graph, I mean this function over the interval from minus pi over 2 to pi over 2, this is an open interval. Actually, it takes all the possible values in its range, that is from minus infinity to positive infinity. Actually, it should be just open interval, it's not closed here. So now we are going to define the inverse functions of these functions over the given intervals. And also actually here we have three more. They are just reciprocals of those functions. Cotangent is 1 over tangent, and the second is 1 over cosine, and the cosecant is 1 over sine. And also for cotangent function, if you consider its graph over the interval from 0 to pi, again here we have open interval, right? If the function becomes, what is it, a one-to-one, and assumes all its values in its range, and that's why we can actually, it makes sense to define its inverse over the interval from 0 to pi. And how about second function? If you look at the graph of the cosine function, right, here we have cosine function from 0 to pi. And when it is pi over 2, cosine is equal to 0. And we don't have 0 division. 1 over 0 actually it goes to positive infinity. So actually, anyway, there's also second function. We can define it as inverse over the interval from 0 to pi over 2, union pi over 2 to pi, because at pi over 2, second function is not defined. But over this, the interval, the function is 1 to 1. And how about it is range? Range is minus infinity to negative 1, right? It's coming from minus infinity to negative 1 and 1 to positive infinity. 1 actually is equal to 1, when is x is equal to 0. Anyway, for cosecant function also in similar way, actually, we can define how to say, bring a restriction to this domain, so that if you just consider this function over the interval from minus pi over 2 to 0 or 0 to pi over 2, our function is a 1 to 1, so that it makes sense to define its inverse over this domain. So its range is minus infinity to minus 1 and 1 to positive infinity. Since these restricted functions are now one-to-one, they have inverses, which we denote actually this subscript notation -1. Okay, it's not a power or exponent. It's just how they read this. Y is equal to sine inverse of x, or simply also we can use arc sine of x, and there's a story behind using this arc, but we are not going to talk about here. So cosine inverse of x, tangent inverse of x, and the cotangent inverse of x. That means that here, if you're given this function, right, y is equal to sine of x, right? So here, usually, how do you find the inverse of the function? We need to interchange x and y's, right? So here we have x, and here we have sine of y. But now, how can I express this one in terms of x? We don't have any algebra to do this one, and that's why we have to use new notation. So this y is read as sine inverse of x. Okay, so here these are the graphs of the inverses of those functions. Because as you remember from the first part of this chapter, to draw the graph of the inverse of the function, right, we have to just reflect its graph about the line y is equal to x. So here at the time, we know that for sine function, the first one, sine function, we know that its range is from -1 to 1. So now, since we are talking about inverse, its actual range becomes domain, its domain becomes range. So now domain is from -1 to 1. And how about its range? It is from minus pi over 2 to pi over 2. And how about cosine function? We know the cosine function's range is from -1 to 1, and it is domain is from 0 to pi. This is how we define this. And here, so the domain actually becomes range, range becomes domain. So here, the domain of the inverse of cosine function, that is from -1 to 1 inclusive, and its range is from 0 to pi. And in a similar way, you can just have a look at C, that is the graph of the tangent function, and the second inverse function, cosecant inverse function, and cotangent inverse function. Okay, so now after we define this, here we are going to talk about what is it, their derivative. How do we differentiate the inverse of the functions? Because their derivatives appear in some integrals, in some applications. That's why it makes sense to actually make a study over these concepts. So before we continue, actually proceed to our differentiation, let's consider a few examples as a warm-up, and after that we will talk about the derivatives. So the arc sine and arc cosine functions. So y is equal to sine inverse of x is the number in minus pi over 2 and pi over 2 for which sine of y is equal to x. That is a definition, how we are defining the inverse of sine function. And how about for cosine? Y equals cosine inverse of x is the number in 0, I mean a number and the interval from 0 to pi for which cosine of y is equal to x. That is how we define this. For example, using this definition, how do we evaluate the following? The sine inverse of -3 over 2, right? And we know that that is an angle, right? Let's say that angle is theta or alpha. It doesn't matter, actually, I can use any letters. So let's say it is alpha. Okay. All right. So at the time, by definition, what is it? It is here, it's not specified this equation, right? Sine of alpha is equal to square root of 3 over 2, where this alpha is a number over the interval from minus pi over 2 to pi over 2, right? So we know that in the first quadrant, right, that is from 0 to pi over this sine function is positive. And also, how about the second quadrant? And we know the sine function is, what is it? Odd function. Now from here, we know the sine of pi over 3, that's equal to square root of 3 over 2. So from here, then what is alpha? Alpha should be equal to minus pi over 3. Okay, so alpha is minus pi over 3 because this function is defined here, right? The alpha, right, is here. So how about the second one? Cosine inverse of minus 1 over 2. So let's say that's equal to beta, right? Now from here, actually we know that by definition, which means that the sine of beta should be equal to negative 1 over 2. Now immediately from here, what is beta? Beta is an angle over the region or in the interval from 0 to pi, right? From 0 to pi. You see here the equation, the second one, just directly using the definition of cosine inverse. Now from here, uh, actually it's not sine. Why did I write sine? It's cosine. So here we have cosine of beta is equal to negative 1 over 2. So beta equal is from 0 to pi. Right, we know that in the first quadrant, cosine function is positive. So in the second quadrant, and also we are going to use this identity, cosine of pi minus beta is equal to minus cosine of beta, right? So from here, we know the cosine function that's equal to 1 over 2 where? And 1 over 2 in the first quadrant when beta is equal to 60 degrees, which is equal to pi over 3. Now from here, then what is cosine? Cosine function here minus cosine of beta, right? If beta is equal to pi over 3, so minus cosine of pi over 3, that's equal to minus 1 over 2. So that's equal to cosine of pi minus pi over 3, which is equal to, it is 2 pi over 3. So cosine of 2 pi over 3, which implies that here our beta is 2 pi over 3. So the value of this actual thing, cosine inverse of minus 1 over 2 is equal to 2 pi over 3. And how about in example C? In example C, suppose that inside this one, let me just denote this by x. At the time, by definition, here we have cosine of x is equal to square root of 2 over 2. And we know that here actually our x is uh, what is the angle in the interval from 0 to pi inclusive, right? So from here, what is x then? This x is equal to pi over 4. We know the cosine of pi over 4 is equal to square root of 2 over 2. So now if I substitute this into the original equation, then here we have sine inverse of pi over, what is it? Square root of 2 over 2, that's equal to pi over 4. So here we have pi over 4, which is equal to square root of 2 over 2. So that thing is equal to square root of 2 over 2. Okay, identities involving arcsine and arccosine. These identities are important because actually it just make our, how to say, work much shorter. So especially if you're going to find, for example, the integrals and for example, let's say the second one, for example, sine inverse of x plus cosine inverse of x, that's equal to pi over 2, right? So now if you just take from here, let's say from here, I can just write here sine inverse of x is equal to pi over 2 minus cosine inverse of x, right? So now if you differentiate both sides, what happens here? Here means that here, if you differentiate both sides with respect to x, let me just use prime notation here. Pi over 2 is constant. So here we have minus cosine inverse of x prime. So which means that the derivative of sine inverse of x is just negative of derivative of cosine inverse of x. So once we get the formula for sine inverse, we don't have to go through that long process to get the, what is the derivative of cosine inverse. Just multiply by -1, we get the derivative of cosine inverse. So now, if you just look back to this question again, why actually these identities are true. So if you just look at the first one, here x is any real number or any radian or angle, doesn't matter. Here, so cosine inverse of x plus cosine inverse of minus x is equal to pi. Let me just draw a line here. So the first one, cosine inverse of x plus cosine inverse of minus x, that's equal to pi. Suppose that actually this part is equal to alpha. Okay, and how about this one? Let's say it's equal to beta. By definition, what is it? That is cosine of alpha, that's equal to x. The second part is cosine of beta is equal to minus x, right? So what is the difference here? The values of this x and y, right? I mean, cosine of alpha and cosine of beta, they only differ by -1. So by using the definition of cosine, and again, if you just consider this in the unit circle, let's say this x and this y, right? And suppose that is our unit circle. And what is cosine of alpha? Cosine of alpha is, we know that that is the projection of the point, right, on the x-axis. So we are talking about this angle is alpha. So this one is cosine of alpha. Actually, that is x. This one is, what is it? Let's say this x and y. And how about it is reflection about the y-axis? So this point is minus x and y, right? And how about this angle? Let's say starting from here. Let's say this angle is alpha also, right? This point, it is cosine of beta, right? Now from here then, what is beta here? If you notice here, beta is just 180 minus alpha, right? So from here, beta is equal to pi minus alpha. So if you substitute there now, it is alpha plus beta. What is beta? It is pi minus alpha. It is always equal to alpha. That's why cosine inverse of x plus cosine inverse of minus x is always pi. And how about the second part? For the second part here, again, using the same thing, let's say alpha is equal to sine inverse of x. And beta is equal to cosine inverse of x, right? From here, what is x? X equals sine of alpha. And how about, what is it? The second one, what is x? X is equal to cosine of beta. And we know that when sine of alpha is equal to cosine of beta in a right angled triangle, and let's say this angle is alpha, and this one is A, and this one is C, right? This one is B. What is cosine of alpha? That is A over C. And how about cosine of, let's say this, if this one is beta, at the time it will be, what is cosine of beta? That is A over C again. So which means that actually cosine of alpha is equal to, I mean, sine of alpha is equal to cosine of beta if and only if this alpha and beta are complementary angles, which means that this alpha plus beta must be equal to pi over 2. So which means that sine inverse of x plus cosine inverse of x is always equal to pi over 2. Okay. Inverses of tangent of x, cotangent of x, secant of x, and cosecant of x. And here, y equals tangent inverse of x is the number in the interval from minus pi over 2 to pi over 2 for which tangent of y is equal to x. And y equals cotangent inverse of x is the number in 0 from in the interval from 0 to pi for which cotangent of y is equal to x. Okay, again, using this definition from here, so that is equal to, let's say, alpha. Now, from here, what is alpha? Alpha is the angle in the interval from minus pi over 2 to pi over 2. Now, from here, what is tangent of alpha then? Tangent of alpha is equal to minus square root of 3, right? So we know that in the first quadrant, tangent is positive. So the angle is not in the first quadrant. So it's actually defined from minus pi over 2 to pi over 2, right? So then the tangent, we know that when is equal to square root of 3. And also here, I'm going to use this identity. We know the tangent of minus alpha is equal to minus tangent of alpha, right? So when tangent is, what is it? It's square root of 3. That is when the angle is 60 degrees. So from here, what is alpha? Alpha is equal to then minus pi over 3, because tangent of pi over 3, that's equal to square root of 3, and the tangent of minus pi over 3, that's equal to minus pi over, pi over 3. So the value of the first expression is minus pi over 3. In a similar way, how about the second example? Let's say that's equal to beta. And notice here that from the definition, what is beta? Beta is the angle in the interval from 0 to pi. So from here, cotangent of beta is equal to minus 1 over square root of 3, right? And also, actually, we know that the same property actually works for cotangent. Cotangent is also an odd function. Cotangent of minus beta is equal to cotangent of beta, right? Now from here, so cotangent of beta, right? So that's equal to minus 1 over square root of 3. And in the first quadrant, that is positive, right? So it must be the second quadrant. From here, we know that cotangent of beta, that's equal to, what is it? 2 pi over 3. And how do you know that? Immediately you can just draw a reference right angle triangle. So if this angle is, let's say, this beta, since we are talking about cotangent, right? It is adjacent side to opposite side. That is square root of 3. So which means that the hypotenuse is equal to 2, right? So from here, when actually we have this relationship, that means that here the sine of, what is it? 30 is equal to 1 over 2. So this angle should be, what is it? Pi over 6, which means that this beta is equal to pi over 3. So since it is in the second quadrant, that is pi minus pi over 3, that's equal to 2 pi over 3. And how about question C? And suppose inside, let me just denote this by y. Okay, so at the time, here we have sine of y is equal to minus square root of 3 over 2. We know the sine of 60 degrees, that's equal to square root of 3 over 2. And this inverse sine function is defined over the interval from minus pi over 2 to pi over 2. That implies that this y should be equal to minus pi over 3. That's the first step. And the second step, now if you substitute there, cotangent of the inside, that's equal to minus pi over 3, right? So that's equal to minus cotangent of pi over 3. Now from our triangle here, that is pi over 3, right? What is pi over 3? It is, what is it? Adjacent side over opposite side. That's equal to minus 1 over square root of 3. All right, these are just introductory parts. Now let's talk about the derivative of these inverse trigonometric functions. We'll just start this with the sine function. On the right-hand side, as you see, that is the graph of the inverse, sine inverse function. And as you see here, the domain is from -1 to 1, and the range is from minus pi over 2 to pi over 2, right? And what is the geometry interpretation of the derivative? We know that here, if you just draw any tangent at any point over on this, what is it? The graph of the function, right? And the derivative gives the slope of the function or the slope of the tangents at that point. So now here, the sub formula is, if you differentiate the sine inverse, that's just equal to 1 over 1 minus u squared and du dx. Okay, why is it so? And because actually math for most part, right, the memorizing is not suggested. So we have to try to understand the idea how we obtain this formula. So here, since by the definition, suppose that y is equal to sine inverse of u. Okay, now I can just do this for x. You know that if it is u, you have to just add this du dx, right? So suppose that we are talking about this x, let's say sine x, right? So by definition, what does it mean? It means that here that x is equal to sine of y. So now still keep in mind that y is a function of x here. Y is a function of x. So here y is the function of x. Now if we differentiate both sides with respect to x, right? So that means that I'm going to differentiate both sides with respect to x. The derivative of x with respect to x, that's equal to 1. On the right hand side, we have a composite function, right? Sine of y is a function of x. And using the chain rule, that's equal to y prime times, right? Now I have to differentiate sine, so that is equal to cosine of y. Now from here, what is y prime? Then y prime is equal to 1 over cosine of y. That's it. But now, if we want to express our result in terms of x, right, how can I do that? Since using this relationship, the sine of y is equal to x, right? So now if I just draw our reference triangle, and let's say this angle is, it is y, right? The sine function is equal to what? Sine of y is equal to x means opposite side is equal to x, hypotenuse is equal to 1. And how about the second shorter side of this right angle triangle? That's equal to 1 minus x squared using the Pythagorean theorem. Now from here then, what is cosine of y? Cosine of y is equal to adjacent side, right, over hypotenuse. That's equal to 1 minus x squared, right? And we know that x is, what is x here? X is between -1 and +1. So from here, if you substitute there, then dot, 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 then y prime will be 1 over square root of 1 minus x squared. Okay. And also you may wonder here it is positive because if you look at this graph, right, if you just draw a tangent anywhere on this graph, it's always positive. The slope of the tangent line is positive. So this is how we obtain or differentiate the inverse of sine. That's the one example to the related to this, changing the color. So what is the derivative of this function? Now here, first, let's just identify this u. U is, what is it? That is x squared, right? So this derivative of this function is equal to 1 over square root of 1 minus u squared. That is x squared, right? It's our u is x squared squared. So now I need to differentiate u with respect to x. Our u is x squared. Then now if you simplify this, the derivative of x squared, that's equal to 2x over, and here we have 1 minus x to the power of 4. And how about the second one? Actually, we can just do this one by one. Here we have the product of two functions, and here we have just uh, another function. So if you differentiate this, first differentiate x. So here we have that's equal to sine inverse of x, right? And plus first x. And what is the derivative of sine inverse? That's equal to 1 over square root of 1 minus x squared. Plus, and how about if you differentiate the square root of 1 minus x squared from inside, that's equal to minus 2x times, and the power comes to the front, that's equal to 1 over 2 times 1 minus x squared to the power of minus 1 over 2, because 1 minus 1 over 2, that's equal to minus 1 over 2. So now if you simplify this, here we have sine inverse of x plus, here we have x over square root of 1 minus x squared. And here we have minus this 2, they cancel each other. And this 1 minus x squared to the power of minus 1 over 2. That is in the denominator square root of 1 minus x squared. In the denominator, we have x, right? These two terms, they are exactly the same. So what we have here is sine inverse of x. Okay. Well, what you have to remember here is that means that if you differentiate this function, right, that f, that is f prime is equal to this, which means that, so we will see that if you integrate this sine inverse function, sine inverse function dx, because in different way we can integrate this, but by integration by parts, but we have not studied that method yet. So now, in case if you have to calculate this one, what is it? That's equal to x times sine inverse of x plus square root of 1 minus x squared, and here we have some constant c. Okay, so the indefinite integral of this function is this. All right, how about the tangent function? So also for tangent function, okay, just using the simple definition, and we are going to get the formula here. So suppose that by definition, what is it? That's y is equal to tangent inverse of u. But here again, I'll just consider this x. And after that du dx, we can just add this. So what is it? By definition, that is the, what is it? X is equal to tangent of y. So now, again, just keep in mind that y is the function of x here. Y is a function of x here. So if you differentiate both sides with respect to x, on the left-hand side, I have 1. And what is the derivative of tangent of y? First, I had to differentiate this y prime, right, from the argument. And after that, differentiate tangent, which is equal to secant square root of y. So which means that here that y prime is equal to 1 over secant square root of y. Okay. So now how can I actually express it in terms of the original function? I'm just going to use this, what is it? Identity. So we know that 1 plus tangent square root of y is equal to secant square root of y, right? And also, what is tangent of y? Tangent of y is equal to x. So that's equal to, which is equal to 1 plus x squared. That's equal to secant square root of y. So now if you simplify here, then y prime, the derivative of tangent inverse, inverse of tangent, that's equal to 1 over 1 plus x squared. Okay, so now immediately from here now, you will see that if you want to integrate the functions in this form, 1 over 1 plus x squared dx, that is just simply tangent inverse of x plus c. Okay, and also if you look at the graph of this inverse of tangent function, right? And if you just draw any tangent there, right? The angle between the positive direction of the x-axis and the tangent, it is less than 90, greater than 0, which means it's always positive. That's why it's always here 1 over 1 plus x squared. It always produces positive value. Let's see two examples related to this. Calculate the following derivatives. The derivatives of the inverse of tangent. So from the first one, we know the derivative of tangent function, and suppose that, let's say this one is, okay, let's say this u function, u of x, okay. And at that time here, we are just going to differentiate this one, right? Here we have natural logarithm of u of x here, and I need to differentiate this. And we know how to differentiate that. That's equal to u prime over u, right? So from here equals, what is u? U is tangent inverse of x, or just x. If we're only x, we don't have to write parentheses here, x. And what is the derivative of tangent inverse? That's equal to 1 over 1 plus x squared. So now if you simplify this, that's equal to 1 over 1 plus x squared. And here we have tangent inverse of x. Okay. And how the second one, here we have tangent inverse of natural logarithm of x, right? So from here, suppose that this function is u, right? At the time, what is the derivative of this function? 1 plus 1 over 1 plus u squared du dx. So that's equal to 1 over 1 plus u squared, that is natural logarithm of x squared, times, now we have to differentiate u. And what is the derivative of natural logarithm of x? That's equal to 1 over x. So that's equal to 1 over, here we have x, 1 plus natural logarithm of x squared. Just write like this. All right. How about the derivative of y equals secant inverse? Again, on the right hand side, the graph of this secant inverse is given. And if you just put your pencil on the paper, for example, let's say, as I say here, the slope of the tangent is always positive because the angle between the tangent line and the positive direction of the x-axis, it is between 0 and pi over 2, which means that the slope of the tangent is positive. So here again, by the definition, suppose that I suppose it's given that here y is equal to secant inverse of u, right? From here, what is u? Maybe I can just do this in terms of u. So which means that here u is equal to secant of y. And keep in mind that u is a function of x. So now if you differentiate both sides, right? So if you differentiate both sides with respect to x, on the left-hand side, what do we have here? On the left-hand side, I have du dx, right? On the right-hand side, what is the derivative of secant function? That's equal to secant of y times tangent of y. And here we have dy dx, right? Because the derivative of secant function is secant of x times tangent of x. So here, y is a function of x. That's why here we just write here, what is it? Dy dx. Because y, right? Y is a function of x. Okay. So now from here, I'm going to find dy dx, right? So from here, what is dy dx? Dy dx is equal to, on the left hand side, I have 1 over secant of y times tangent of y, and times here we have du dx. So the problem here is now I need to find secant of y and tangent of y in terms of the original function. And we know the secant of y that's equal to u, right? Now we need to find tangent of y. How can I find this? We know that, again, secant square root of y is equal to 1 plus tangent square root of y. Now from here, tangent square root of y is equal to secant square root of y minus 1. If you just take the square root of both sides, then here we have tangent of y is equal to plus minus square root of secant square root of y minus 1. And we know that the secant of y is equal to u. So if I substitute u here, we have plus minus square root of u squared minus 1. Okay. So now, which one should we take? It is plus or minus? Again, we know that actually the derivative of y with respect to x, it gives us the slope of the function, right? As you see here, the slope of the function is positive, and that's why it must be positive. So here we have then that's equal to 1 over secant of y, that's equal to u. And here, all right, here I'm just going to write here absolute value of u, and here we have u squared minus 1. Okay, and here we have du dx to guarantee that it must be always positive. Okay, example for secant function. Let's consider this example, secant inverse of, what is it, 2x plus 1. Now from here, if you differentiate this by using the formula, what is it? 1 over absolute value of u times square root of u squared minus 1 du dx. So from here, our u is 2x plus 1. And also from here, we know that u prime of x, that's equal to just 10. So that's equal to 1 over absolute value of 2x plus 1 and square root of, here we have 2x plus 1 squared minus 1. It's quite long. And here I need to differentiate u prime, that's equal to just 2. So I can just write here, it is 2. Okay. All right. And how about the second one? Okay, here, if you differentiate the first part, that's equal to 2x, right, minus 1 over 2. Anyway, here that's equal to 2 times x. And here we have minus 1 over 2 because the power comes to the front. It is not minus 1 over 2, just 1 over 2. It's just 1 over 2 times, here we have 1 over square root of x squared minus 1 minus, and how about the second of x? That's just equal to 1 over absolute value of x square root of x squared minus 1, right? So now this x cancel each other, right? Here we have x, that's equal to, here we have x over square root of x squared minus 1 minus 1 over absolute value of x square root of x squared minus 1. So now we can just get the answer. For example, if x equals positive, right? What happens here? Let's say the first case is, suppose that x is positive. At the time, absolute value of x, right, that's equal to x. So from here, then let's say here we have the function is u, y, okay? Then y prime will be equal to, the common denominator is x times square root of x squared minus 1. So in the numerator, we will have here, what is it, x squared minus 1 over, here we have x times x squared minus 1, okay? And of course, when you just say that x is positive, we have to also keep in mind that x squared minus 1 must be positive, right? Which means that x is between 0 and 1 here. Let me just write like this. Because here, x is between 0 and 1. Okay, so which is equal to square root of x squared minus 1 over x. And the second one is, how about if x is between -1 and 0? So at the time, absolute value of x will be negative x. From here, then y prime will be equal to common denominator x squared. But because of this absolute value of x, it will be minus, with minus minus, it is plus. So here we will have x squared plus 1 over, here we have minus x times square root of, okay, not minus x, it's just x. Square root of x squared minus 1. So which is equal to, that's it. I think we have nothing to do with this. Okay, let's simplify this. So, and using these properties, inverse function, inverse co-function identities, we know that we have already proved that sine inverse plus cosine inverse, that's equal to pi over 2, which means that if you want to differentiate the cosine inverse, just multiply the derivative of sine inverse by -1. Also for cotangent, the same thing. For cosecant, the same thing. Okay. Then after that, using these things, we can actually, anyway, summarize the derivatives of the inverse trigonometric functions. As see here, the first three, these are important, and others using the identity, we can obtain them. Okay, and using also this integral, I will stop this video here. You can practice the rest of the questions. Maybe if I have time, I'll make another short video about these integrals. Okay, thank you very much. Bye bye.